Okay, Chipu Osakwe, you're welcome. Good afternoon. If you're online, say hi so we can start. Hello, everyone. Welcome to today's class. Yesterday, we looked at area and volume expansivity, and today we're going to look at real and cubic expansivity, okay? So that you'll be able to understand the difference between linear area and volume expansivity compared with real and apparent cubic expansivity. All right. Davida, you're welcome. Nakuzoyeka, you're welcome. Thank you for coming. All right, put it down. Let's proceed. When Ngozi, I just join us today. You're welcome. Rosemary, you're welcome. Juana Raymond, you're welcome. It's the first time I'm coming for this class, this holiday. All right. Please take it down. Let's proceed. David, is it okay now? Are you done? Is it clear now, Christina? Christina, is it clear now? Is it better? Is it clear? Christian, have I added it to the group? Okay. Have I added it to the group, Christina? Okay. Just type in your number now. Let me take you down. So I'll add you after now. I thought I've added you yesterday. Let me put it down. All right. So can we proceed? All right, so let's look at the real and apparent cubic expansivity. Now, the real cubic expansivity, gamma r, remember that cubic means what? Gamma. So if I say real, I will write gamma base real, that's base r, okay? Of a liquid is the increase in volume per unit volume per degree rise in temperature. So this is the same definition as the volume expansivity, okay? Now let's go to apparent cubic expansivity. The symbol is gamma A. Is the increase in volume per unit volume per degree rise in temperature. This definition is not complete. When the is heated. Sorry, I have to clean and write again. All right, so this is the correct definition. It is the apparent cubic expansivity gamma A of a liquid is the increase in volume per unit volume per degree rise in temperature when the liquid is heated in an expansible vessel. So what am I trying to say? If you heat a liquid inside a container and the container is an expansible vessel, the container itself is going to do what? Expand as a result of the heating. Then the liquid inside the container is equally going to expand. Now, for you to be able to know the real expansivity of this liquid inside the container, you're going to consider the apparent expansivity of this container and the expansivity of the vessel. Is that clear? Now, for you to know the real cubic expansivity of a particular liquid, you're going to consider the apparent cubic expansivity of that liquid plus the expansivity of the container, because that container is an expansible vessel. Is that clear? All right, put it down. Yala Esther, you're welcome. Expansible vessel is a vessel that can expand once heated. It's a container that can expand once heated. Olachi, I did not see you yesterday. You're welcome. How are you today? Is Kewa here? Son, I can't see the number. I can't see it. Christian, have you chatted me on WhatsApp? Have you? Christian, have you chatted me on WhatsApp? Okay. So I will check and add you. Okay. I think I've added some last night. So I don't know if you're among those people that I added. So we'll check it out. Now look at this. Look at this container inside this liquid inside this container. If I want to know the expansivity of this container, what am I going of this liquid inside the container? And this container is an expansible vessel. So for me to know the real cubic expansivity of the liquid inside this container, because if I heat this liquid, because it's inside this container, the container will expand, the liquid will expand. So for you to know the real cubic expansivity of this liquid inside, you are going to consider the apparent expansivity of the liquid inside this container plus the expansivity of the container. By the time you add them together, it gives you the real cubic expansivity of that liquid. Is that clear? All right. Put it down, please. Let's solve. Let's explain rather. All right, put it down, please. Let's proceed. All right, so let's proceed. The real expansion or expansivity equals the apparent expansion plus the expansion of the container. What am I trying to say? For us to or the expansion of that liquid inside a container, because that liquid is inside an expansible vessel. The container has the ability to expand once heated. So you're going to consider the apparent expansion inside the container and the expansion of the container. When we add them together, that gives us the real cubic expansivity. Is that clear? Now, what is the apparent cubic expansivity? That is gamma what? A. How do we get it? The apparent cubic expansivity gamma A is equals to mass of the liquid expelled divided by mass of liquid remaining multiplied by temperature rise. Now, how do I mean? When you heat, let me let me take an example, an expansible vessel. When you heat a liquid that can expand, and once the liquid is heated, it expands. Then after expansion, it's going to do what? Some of the liquid will be lost through the process of evaporation, so it's going to reduce in size. For example, the mass of the liquid before it started heating happens to be what? 50 gram. Now after heating it for like 10 minutes over a certain temperature, you're going to have this M1. The second mass is going to be what? Will be reduced. You might be getting 48.5 grams. Why is this so? Because some liquid has been lost through the process of what? Evaporation. Because once you heat, it's going to do what? Evaporate. So that is why the first mass is always greater than the second mass. Now, how do you know the mass of the liquid expelled? By the time you subtract this remaining from the one that was there before we started heating, you can now know the mass of the liquid that has expelled. I hope that is clear. All right, now the mass of the liquid remaining becomes this, they multiply by the rise in temperature or the change in temperature. So the same is applicable to the volume of the liquid expelled over volume of liquid remaining multiplied by temperature rise. So if you use this method, you're going to get this apparent cubic expansivity. Now for the expansivity of the container, we all know that gamma will never be given, like I told you, but we can have alpha. If you are given linear expansivity, just multiply by 3 to get this volume expansivity, which is this one. Do we understand? So you're going to use this method to solve for the apparent weak expansivity, and then you're going to multiply the linear expansivity by 3 to get the expansivity of the container. Then when we add the two of them together, it's going to give us the real cubic expansivity of that liquid. Is that clear? All right, let's see how we can solve example to make you understand better. David, is it clear now? Okay. All right, I say that if you're looking at the expansion of real expansion or real expansivity, we are going to put in consideration that liquid we are going to heat. And you can't heat liquid with your bare hands, no. For it to be able to heat a liquid, you must put it inside a container, right? And if that container happens to be an expansible vessel, what are you going to do? You're going to consider the real expansion of that liquid. I'm going to consider the apparent expansion of that liquid inside the container itself. Now let me do an illustration again. I said I want to heat this liquid inside this container. How do I know the real expansivity of this liquid inside this container? Because this container can expand once heat is applied to it. So we are going to do what? Heat this container. After heating the container, we're equally heating the liquid. expansivity of this liquid inside this container, I'm going to consider the apparent cubic expansivity of this liquid inside the container and the expansivity of the container. Is that clear? Now, this is the apparent cubic expansivity. Apparent means it is inside. Apparent cubic expansivity of this container of the liquid plus the expansivity of this container. Is that clear? Now, and I said that when we are heating the liquid, the mass is going to reduce. Why? Some of the liquid is being lost through the process of what? Evaporation. I said, for example, we start when the mass M1 is given as 50 gram. Now, after heating to a certain temperature, process of evaporation, so we're going to have the second mass to be 48.5 grams. Is that clear? Is that okay? Now, for us to be able to know the mass that has been expelled, we're going to say that the mass of liquid expelled is equals to the original mass before heating and the mass remaining. By the time you get the subtraction, you know the mass that has done what? That has expelled. Is that clear? Now, with this formula, we can get the apparent cubic expansivity. Now, for the expansivity of the container, remember that gamma cannot be given, but we may be given alpha. So gamma is equals to 3 alpha. By the time you multiply alpha by 3, you're going to get what? Gamma. Then that is what you're going to put here. Then you now add both of them together to get your real cubic expansivity of the liquid. Is that clear? So let's solve an example. All right, put it down, let's solve. Please copy fast, let's solve. Copy fast and indicate that you are done. Let's solve. The number close to 6, this is per Kelvin. This is per Kelvin, right? Raymond, you are done, okay? Christian, you are done, okay? So let's proceed. The question says a density bottle holds 250 grams of liquid at 30 degrees C and only 248.5 grams. Sorry, this is grams. 248.5 grams, okay? At 60 degrees C. Find A, the apparent. Find A, the apparent. B, the real cubic expansivity of the liquid. If the linear expansivity of the material of the bottle is 0.000006 per Kelvin. Let me go again. A density bottle holds 250 grams of liquid at 30 degrees Celsius and only 248.5 grams at 60 degrees Celsius. Find A, the apparent cubic expansivity, and B, the real cubic expansivity, if the linear expansivity is given as this. Now, for us to solve, let us set our parameters and solve. The first mass happens to be my what? My M1, which is 250 grams, okay? And my theta 1 is equal to 30 degrees C, okay? Then my second mass is M2, which is given as 248.5 grams. Now, my second temperature is equal to what? 60 degrees C, right? And we are given alpha to be 0.00006 per Kelvin. Now, the first question we are going to solve is to solve for the apparent cubic expansivity. Then, which is my what? My gamma A. And what is the formula? Mass of the liquid expelled. That would be M1 minus M2. Then divided by M2 what? Theta. Is that clear? The apparent cubic expansivity, gamma A, is equals to M1 minus M2 all over M2 theta. Now, what is my theta? My theta is the difference in temperature, okay? So, my gamma A is equals to, what's my M1? 250 minus my M2 is what? 248.5 divided by my M2 is 248.5 multiplied by temperature is what? 60 minus 30 is going to give us what? 30. Okay? Alright. So I can work it out, or I will say bracket 60 minus 30. Is that clear? So let us subtract and see what we have. 250 minus 248.5. I will have gamma A to be 1.5 all over. Now, 248.5 multiplied by 60 minus 30 is 30. I'm going to have 7455, right? Gamma A is equals to 1 by 7. What do I have? Going to have 2.012 times 10 raised to the power of what? Minus 4 per Kelvin. And this value is for apparent cubic what? Expansivity. Is that clear? It's for apparent cubic expansivity. All right. Now let's move into the real cubic expansivity. If you have questions, you can ask. All right, Christian, I did not change the grams to kilograms. Reason is because it's going to cancel each other. Okay, kilogram cancels kilogram. That is why the unit of apparent cubic expansivity is per Kelvin. Okay, kilogram cancels kilogram. Olachi Ajako, can you see it now? Is it clearer now? Is it clear now? Olachi, is it clear now? All right, Christina, in this question, we are dealing with liquid. We are dealing with liquid, expansion in liquid. But in the previous one we did, we are dealing with expansion in solid. Olachi, is still not clear now. Christina, do you understand? This is in apparent and cubic expansivity, we are dealing with liquid. When we are heating liquid inside container, that is what we consider to be apparent. Okay, so this is under liquid, while the previous one is under solid. See the difference? Solid has length, breadth, and height. Okay, Ajok, is it clear now? All right. When I put it down, let's proceed. All right, please don't forget to go to my Facebook and TikTok and follow me. All right, go to my Facebook and TikTok and follow me with the same name, Jossy Science Academy. Okay, just go there and tap follow. Start following me, right? Okay, don't forget that. Now, for us to solve for the second one, we are looking for the real cubic expansivity. Now, for us to get the real cubic expansivity, the real cubic expansivity gamma r is equals to the apparent cubic expansivity plus the expansivity of the container, right? Okay, now this apparent cubic expansivity is what we have already gotten now. Now we are going to put it, but then we need to get the expansivity of the container. This expansivity of the container, which is gamma. Remember that gamma is equals to 3 alpha, right? Now let's multiply our alpha, which is given as this 0.000006. Okay, with the help of our calculator, let's work it out. 3 times 0.000006. So we have 1.8 times 10 to the power of what? Minus 5 per Kelvin. Is that clear? Now, since we have gotten that, we are going to substitute it here plus the apparent, which we have gotten earlier, When we add them together, it's going to give us the real cubic expansivity. So my real cubic expansivity is equals to apparent cubic expansivity plus expansivity of the container. Alright? My real cubic expansivity is equals to, my apparent is 2.012 times 10 raised to the power minus 4. I hope I'm correct. Let me check. Yes. Now plus my expansivity of the container 1.8 times 10 raised to the power minus 5. Clear. So let's add it together. 2.012 exponent minus 4 plus 1.8 exponent minus 5. So my real cubic expansivity is equals to 2.192 times 10 to the power of what? Minus 4 per Kelvin. Is that clear? Do we understand? We have gotten our apparent cubic expansivity. For us to get the expansivity of the container, we now multiply by 3 alpha to get this. Then we now add them together. And we got our answer to be 2.192 and 10 raised to the power minus 4 per Kelvin. Put it down. I hope that is clear. If you don't understand, you can let me know. Put it down fast. Let's proceed. Christiana, it won't be power minus 6. Look at it now. Even if you multiply 3 times 6, that is 18. If you change that 18 to standard form, that will be 1.8 times 10 raised to the power 1. So that one has reduced the power to make it to be minus 5. Okay? Esther Iyala, say you don't understand. Where do you not understand? Let me go back and explain. Ngozi, say you don't understand. So let me go back to explain. Bongosi, did you understand the previous one I explained? How we got our apparent cubic expansivity? Let me know where your confusion is coming from. Olachi, are you still here? Okay, Esther, this particular one, okay. All right. I said we have gotten the apparent cubic expansivity. Now for us to get the real cubic expansivity of this liquid, the formula for the real cubic expansivity is gamma R, right? It's equals to gamma A plus gamma, right? Now, what is my gamma A? I've gotten it, that is apparent cubic expansivity. Then my expansivity of the container, that is gamma, is equals to 3 what? Alpha, right? Now it's equals to 3 alpha because I said it cannot be given in a question. Rather, there's a relationship between linear expansivity and volume expansivity, and that is what we're just going to use. All right, so they gave us the linear expansivity, which is this. So you just have to multiply out gamma is equals to 3 times this to give us 1.8 power minus 5 per Kelvin. Is that clear? Okay, so for us to get the real cubic expansivity is equals to apparent cubic expansivity plus expansivity of the container, right? Now, what's my apparent cubic expansivity? 2.012 exponent minus 4 plus 1.8 times 10 to the power minus 5. By the time you add them together, it's going to give you what? 2.192 power minus 4 per Kelvin. That is all. Is that clear? The only difference is for you to get this expansivity of the container, which is gamma. Then you add it together to get this. Alright? To get this one. That's all. Esther, hope that is clear. So sorry. All right, Christiana, I said I should explain why it is that. Okay, let me do just that. You know that this is the same thing as saying 3 multiplied by 6, right? Times 10 raised to the power minus 6, right? So if that is the case, 3 times 6 is 18. 18 times 10 raised to the power minus 6, right? Okay, now 18 is the same thing as saying 1.8 times 10 raised to the power 1, right? Times 10 raised to the power minus 6, right? By the time you work on the powers, you are going to get 1.8 times 10 raised to the power 1 minus 6 is what? Minus 5. And that is why we have the answer to be 1.8 times 10 raised to the power minus 5. Is that clear? All right. I just added it with calculator. Do you have calculator there, Christiana? You have calculator. Let me teach you how to add. Do you have calculator there? All right, I can teach you manually how to add. So let me teach you manually how to add. Since you don't have calculator. Okay, let's say if I add this two, we have 2.012 times 10 raised to the power minus 4 plus 1.8 times 10 raised to the power minus 5. Right? Let me do normal addition. I hope you can hear me. Can you hear me? All right. Normal addition. This is the same thing as saying 0.0002012. Okay? All right. Plus 0.0000. Okay? Am I right? 1, 2, 3, 4, 1, 8. Am I right? Okay. Now let me do it well so you don't get confused anymore. 0, 0, 5, 1, 8. Is that clear? All right. Now, nothing is here. I'm just going to bring down what? 2. 1 plus 8 is going to give us 9. 0 plus 1 is going to give me 1. 2 plus 0 is going to give me 2, right? 0, 0, 0.0. Is that clear? So, changing it to standard form, I have 4 zeros before the number, so I'm going to raise the power of minus 0. I'm not raising it to the power of minus 0 because 0 starts before the number. That is just to change the standard form. Okay? I'll go this way. 1, 2, 3, 4. Right? So this is 2.192 times 10 raised to the power of minus 4. Then I'll put the units. That is how it was added. Is that clear? Christina, is that clear now? All right. Christina, is that clear? Christina, is that clear? Let's go to another question. So let me give you this one to try, okay? Let me tag it as classwork. All right, a density bottle contains 44.24 grams of liquid at 0 degrees Celsius and 42.02 grams at degrees Celsius. Calculate the real cubic expansivity of the liquid, right? Now, in brackets, we are given the linear expansivity of glass to be 1.0 times 10 raised to the minus 5 per Kelvin. All right, you can attempt it. Choma, have you gotten the question? Obuchi, so you are just joining us for the first time. Okay, I should repeat what I just said. A density bottle contains 44.25 grams of liquid at 0 degrees Celsius and 42.02 grams at 50 degrees Celsius. Calculate the real cubic expansivity of the liquid. In bracket, the linear expansivity of glass equals 1.0 times 10 raised to the minus 5 per Kelvin. All right, please. So let's see. right? You say you got 1.091 power minus 3 per Kelvin. All right. Okay, so who else is solving? Let's confirm what she did, whether she's correct or not. So who is correct? Send me your answers, please. Let's solve. All right, let's solve together. A density bottle contains 44.25 grams of liquid at 0 degrees Celsius and 42.02 grams at 50 degrees Celsius. Okay. Calculate the real cubic expansivity of the liquid. Now we are given the apparent expansivity of glass to be 1.0 power minus 5 per Kelvin. Now, how do we solve this? Let us set our parameters. Our first mass, M1, is given as 44.25 grams. Then, the first temperature happens to be 0 degrees Celsius. Our second mass, which is 42.02 grams. And the second temperature happens to be 50 degrees Celsius. Now, temperature, that is theta 2 minus what? Theta 1. We have 50 minus 0, which is going to give me 50 degrees Celsius. All right? Now, for us to solve to get our apparent cubic expansivity, that is the first thing we are going to do. Apparent cubic expansivity, M1 minus M2 all over M2 theta, right? Now gamma A is equal to, what's my M1? That is 44.25 minus 42.02. Then divided by what? 42.02 multiplied by 50. Okay? Now let's subtract 44.25 minus 42.02 is equals to 2.23 and divided by 42.02 times 50. What do we have? We are going to have 2101, right? Okay, let's divide and see what we have. 2.23 divided by 2101. I'm going to have my gamma A to be 1.061 times 10 raised to power what? Minus 3 per Kelvin. Okay, this is my gamma A. So the next thing to do is to find my gamma. And my gamma is equals to 3 what? Alpha. That is 3 multiplied by 1 times 10 to the power of what? Minus 5. So it's going to give me 3 times 10 to the power minus 5 per Kelvin. Okay? So if you add it together, gamma R is equals to gamma A plus what? Gamma. Is that clear? Okay, let me top up my ink. Sorry for that. I hope you are following me. Now, gamma R is equals to gamma A, giving us 1.061 times 10 to the power minus 3, then plus 3 times 10 to the power minus 5. Okay? And my answer is equals to, let's just add it together, 1.06 exponent, 0.1 exponent, minus 3, plus 3 exponent, minus 5. And the answer is equals to 1.091 times 10 to the power minus 3 per Kelvin. And this is our final answer. And Christiana, you are correct. An applause for yourself. Is that clear? All right, put it down. Put it down. Do we have question? Any question? Any question? All right, in the absence of no question, we are going to end the class today. I'm going to end it here. I'll drop your assignment in the community. So you go and pick it and solve. You're in the first example. Okay. Davida, what do you mean by zero, please? All right, Christina, when you go to my channel, you're going to see my videos, my playlists, and my community. Go to the community. As soon as I end this class, I'm going to put up an assignment there. So you take it and solve. Okay, that's what I mean. All right, we have come to the class, and don't forget to go to my Facebook and my TikTok and follow me, okay, on the same name, Jossy Science Academy. Okay, thank you so much for doing that. I'm going to drop an assignment in the community, so don't forget to go there to copy the assignment and solve it and drop your answer in the comment section. The more you solve, the more. I'll see you next time in the next one. Tomorrow I'm going to put up in the group the time for our class because tomorrow is Sunday. Okay? See you next time in the next class. Bye for now. Yes, I'll put it in the group chat, okay? All right. You're welcome. You're welcome. See you tomorrow. Davida, what's your question? You have gone. David, I can hear you. What's your question? Hilda Martins, SS what? Hilda Martins, you're in SS what? SS2. Our SS2 class has ended, so you can go to my channel and search for it. We did temperature measurement today, SS2, so go and look for it. Go and watch the video, okay? At Hilda Martins. Davida, what's your question?